Today I'll talk about some work I've been doing the last few years on singularity formation in Euler equation specifically. So I'm going to try to recap and talk about sort of what's next. Um, so I guess for this seminar, I don't need to go too much into the background. Let's just start from the beginning. So the Euler equation is this. So the velocity field transports itself, and in order to keep the divergence free condition, you put a correction, and the divergence free condition is just the condition that the velocity is incompressible, which means that the flow can never be like this. So this is not allowed. So put an X. So anytime you have a compressing direction, there has to be a decompressing direction in the fluid. And of course, as we know from first course in PDE, this particular type of nonlinearity is kind of dangerous for the long time behavior. So that if you have burgers, just like the 1D version of this, right? Then the derivative can develop a singularity in finite time. Okay, so I should say minus infinity. But remarkably, the incompressibility condition makes this impossible in 2 dimensions, right? So there's a fact. So by the way, this is not for 1D Burger's equation, you have conservation of the L2 norm in the L infinity norm. So it's not only about energy conservation. So there's some structural difference between Burger's and the Euler equation, such that in 2D we have, as many of us know, global regularity. So how do we see that? So important difference between compressible and incompressible fluids is that the dynamics of incompressible fluids are essentially governed by the dynamics of vorticity, right? So if you define the vorticity to be the curl of the velocity field, so in 2 dimensions, and 3 dimensions, this makes perfect sense. In 2 dimensions, we just mean you take the perpendicular gradient, which just means that you view the gradient as a vector, and then you rotate it 90 degrees and dot it with U, and that's the 2-dimensional vorticity. So the vorticity, since the divergence of U is 0, you can recover the whole velocity by the vorticity, right? So there's a fact that if U is divergence free, then we have that the curl of the curl is minus the Laplacian of U, right? And as a consequence, and there's a similar remark you can make in 2 dimensions. As a consequence, so this is the vorticity, then you can recover the whole velocity by U is the minus Laplacian inverse of the vorticity. You take the curl of that. So this is so-called Biot-Savart law. Okay. Now the utility of the curl is that it satisfies maybe a nicer looking equation than the full gradient. So as I remarked back here, the kind of singularity that might occur in the Euler equation, just like for the Burger's equation, that what we expect is that it's a singularity in the gradient, of course, we don't actually know that. It's possible because of the pressure that even the velocity could blow up pointwise, but okay, we don't know that. If it's anything like the what we think, then it's really the gradient of the velocity that develop a singularity. And you know, a nice part of the gradient is the vorticity, because it satisfies this interesting equation. So it's transported and then stretched. Right. So this is called, so the gradient of U is a matrix. So this is just normal multiplication of matrix and a vector. So this is called the vortex stretching. And this is called the transport term. And so the velocity is recovered through this equation. So once you know the vorticity, you recover the velocity. Once you know the velocity, you recover the vorticity. So it's a closed equation, a closed system. So essentially, the vorticity is transported and stretched by a velocity that it itself induces, right? So vorticity is transported and stretched. And okay, the reason, okay, one reason that this is called stretching is that the vorticity grows pointwise along directions of the gradient of u that are expanding. So if you have a expanding direction of the velocity, right? So if you think about the pointwise growth of the vorticity, so if you have to dot the equation with omega, and you have to see when the this bilinear form of omega is positive, right? Those are the points where, at least along trajectories, you are growing, right? Now, if this is positive, so we're talking about the directions of maximal growth are the directions of positive eigenvalues, or the maximal positive eigenvalue of the gradient of u. And in that direction, the velocity is expanding, right? So you can see that the velocity stretches the vorticity. So that's why this is called vortex stretching. At the same time, because of that, what this means is that particles which, so if you have a point where gradient of u is large, and where this is happening, then in the direction of stretching, the particles are also exiting quickly that region, right? So you have like a dual effect because of vortex stretching and because of transport. So there's some kind of inherent regularization effect within the equation. Okay, now let me just recall one thing. So as I mentioned in the beginning, so a necessary and sufficient condition for a singularity to occur from smooth data is that the gradient of u in L infinity, so the quantity that controls the characteristics when integrated in time, and as you approach the purported blow-up time, this should become infinite, right? So this is what controls the regularity of the equation. And very important result that due to Biot-Savart is that you can replace this condition by much more useful condition, which is that just the vorticity pointwise go to infinity. And this is useful because the vorticity equation is much easier to deal with than the full gradient. Okay, so in the last couple of years, in different settings, we're able to show that this is possible for moderate regularity data. It still remains open, so the question that remains open is if the data is C infinity, right? Can star happen for T star finite, right? So this, we recently solved different cases of this. First, with NG Jiang, we considered the case where you replace C infinity by the space of Lipschitz functions intersected with, you need to do a bit more in order to get even local existence. But, and then later we did the case of C1 alpha data. But the full C infinity case, especially on the whole space, remains quite elusive. So I want to talk a bit about sort of the methods that go into constructing singularities and what maybe can happen in the future. Okay, so how do we construct a singularity? Okay, so it's important that we first try to think about the simplest possible settings where singularities occur. So remember that what we're after is growth of the vorticity, right? So really, how do we construct singularity? Another way of asking that question is, how do we get the vorticity to grow in 3D? So we need so first we need a mechanism to grow vorticity. And second, we need some feedback. Right? So once the vorticity grows, it should strengthen the mechanism. Right? And that's essentially how you can have vorticity growth. Now, to understand this, so the first one, I think, it's just a question about the structure of this equation, right? So the Euler equation is this. It's you prescribe what the velocity is. You say the velocity is the inverse Laplacian of the curl of the vorticity, and the vorticity is evolving this way. So this is the 3D Euler equation. But when we think about mechanisms for growth, really we're thinking about, if you have an equation that looks like this, you have a velocity, maybe that you can just come up with it yourself. How can I get the vorticity to grow? Right? What are the kind of shape of the velocity or shape of the motion of particles or whatever that will lead to the vorticity to grow? And then you can, after that, think about how that then affects the velocity itself and how there can be some kind of feedback. Right? So first, let's think about just structurally looking at this equation. how that can happen. Okay, so we want to look at, say, a one-dimensional problem first, just one-dimensional scalar, so just the simplest possible scenario, right? And as I remarked earlier, there's inherent problem with this equation in terms of singularities, in that if you have a point here where if we move to a moving frame, we can assume that the point is stationary maybe, and if you have in order for omega to grow, you need dx of u to be positive at least, right? If you think of it, if we just suppress the transports and go on characteristics and think of this as an ODE, right? If you have an ODE of this form, right? When G is negative, just F decays. When G is positive, F grows, right? So in order for there to be growth, dxu has to be positive at the place we expect for growth to happen. So let's say it's right there. Then that means that the trajectories are being pushed out, right? So dx of u is positive here, means if you move with the velocity of this point, or if you assume the velocity at this point is 0, then the particles have to be pushing out like that. But that means that if a particle, say right here, is supposed to be growing, then it may grow for some short time, but then be pushed away, right? So let me give a nonlinear example where this is actually I'm not just saying something trivial. So let me give an example. So consider this equation. And now let's give a nonlinear example. It means that we say what the velocity is. We say the velocity is just the projection to sine of x of omega. Okay, by which we mean, so it's sine x times the integral, maybe with 1 over pi. Okay, so consider this. We just determine the velocity by one mode of omega. Okay, so this is, in fact, this is a quite reasonable model. It's you can view it as a model of the de Gregorio equation, if you're aware of that, or it's also one of the most simple but non-trivial models that you can have of the vorticity dynamics in 1D at least. And it turns out that so let's think about what's going on. So if we call this lambda of t, then the equation is just dt of omega plus lambda of t sine of x dx omega is omega lambda of t cosine x times omega. Okay, so this is now the equation. It's just a closed equation on omega. And notice that the transport and the vorticity stretching, right? So these are like 1D versions of that. They kind of have the same power, right? This lambda of t comes as a factor in both of them. And that makes sense that they're kind of symmetric, right? And singularity can occur, right? Singularity in this equation occurs if and only if lambda of t, so singularity means in this equation, means that omega pointwise has to go to infinity. But here it also means that this coefficient must go to infinity, right? At some finite time, right? And surprisingly, if you were to cancel, sorry, not surprisingly, if you were to cancel the effect of the transport term, you to just completely forget about this one, then you could easily come up with initial data for this equation, which goes to infinity. Right? It's not very difficult. But once you include the transport term, so I don't know if I can. Oh, I think I can undo what I just did. Okay. So if you put it back, which thankfully you can do using Zoom, then you get the following theorem. If omega 0 is C1, then solution must be global. And this, to prove this, you kind of have to solve the equation and get solve the system along characteristics, and then using the ODE method, and get a closed equation on lambda. When you get a closed equation on lambda, there's very interesting cancellation that occurs that shows you that lambda actually must remain uniformly bounded for all time. Not only does it not go to infinity, but it's uniformly bounded, which is, I think, very interesting fact. Okay. Now, interestingly, if you consider the same equation, if omega 0 is just in C1 minus alpha, just barely below. So remember that for 3D Euler and for this equation also, you have local existence once the vorticity is slightly better than L infinity. But you notice that I put here C1, right? The global existence in C1. And interestingly, if you put spaces on a line, if you say this is like C1, C2, dot, 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 here's C0. In this whole region between C0 and C1, so not including C1, so say I'm in the C alpha range. So if you start going to like more exotic spaces, okay, what I'm saying is not exactly correct, but if you just think in C alpha, then in this whole region in the middle, you have local well-posedness, but solutions may blow up. No global well-posedness. But once you pass C1, you have global well-posedness. So it's a very interesting fact that the local theory and the global theory don't really match up. Right? So the local theory starts at C0. In fact, for that equation, it starts much earlier. But like in Euler, the local theory may start around C0, but then the global existence results may start much later. Right? So it's this is something that one has to keep in mind, that there may be certain types of blow-up that are artifacts of low regularity. Now, it's still very interesting that this can happen, but it doesn't necessarily reflect that there's blow-up for smooth solutions. Now, let me make a second remark on this model, that if you notice the relationship between U and omega is they keep the same parity, right? So if U has certain parity, then if omega has a certain parity, so it means odd or even, then U has to have the same parity, right? But if you, and that, interestingly, that's the key to this global regularity fact. if you change the parity in the equation, right? So if you consider a different Biot-Savart law, so you just consider the same equation. Oh, sorry, but before saying that, I should also make a second remark. Um, another way to have, so this is the case of S1, right? So this is without boundary. So what I'm describing here is there's no spatial boundary, so it's just on the circle. So if you allow yourself to put a boundary, so if we allow, oops, if we allow solid boundary, then it's easy to get around the global regularity. So we can have a singularity for C infinity data. Okay, for a similar type of model, you need to change the equation I wrote was specific to the circle, but essentially the two, as of now, known ways to get out of the global regularity issue is to have data that's below C1 in vorticity, like C alpha, or to have a solid boundary. Then there's no conceptual issue with having a singularity in the vorticity equation. Of course, actually showing it with the real Biot-Savart law is a different story. Now, an interesting third way, out of the regularizing effect of transport. So all of what I said back here is basically due to the fact that if lambda starts growing, so if the vortex stretching becomes more powerful, then the transport has some regularizing effect, which in reality you can only see when you try to solve the equation as of now. Now, another way to get out of this regularizing effect is to change the parity between omega and u. So if you define u, instead of having the same parity as omega, as having the opposite parity, so you take it to be the same projection, but then you add a derivative. So adding a derivative doesn't change anything in terms of regularity in this setting, because it just changes the sign to a cosine, right? Okay, so I'll add the pi this time. Right. Then here you can have so theorem. So solutions. So C infinity solutions can become singular. And this is somewhat surprising if you think a lot about this type of equation. It's not immediately obvious why this small change would. When we think, classically we think about, the vorticity equation as like this, and the velocity is just, one derivative better than vorticity or whatever. But it's not. So we really think about it in terms of regularity and things like that. So the regularity of the map taking omega to the velocity. But it seems that when you think more about the formation of singularities or dynamical questions, the precise structure like parity and things like that becomes actually much more important than the number of derivatives or something like that. Okay. Okay, so just to recap what we just said, so ways to get around transport regularization. One way is to have C alpha data in the direction of the flow. Okay, so if you, as I mentioned, the vorticity tends to, the growth is coming mainly from the stretching term. So if you can remove the effect of the transport in some way or weaken it, then there will have a better chance to get a singularity. And this can be done by taking data that's C alpha in the direction of the flow. So such that, so if omega is like C alpha, so if you think about something like, if you consider u dx omega versus omega dxu, and you think about omega is like x to the alpha, right? U is like x, right? So u is always smoother, or at least 1 degree smoother than omega. Then you see that this term is order alpha, right? Because you just take x dx of x to the alpha, you get a factor of alpha, but this term is still order 1 because it's dx falls on u, so it's order 1. Right, so this is sort of just cartoon of why taking data that's C alpha in the direction of the flow, right? So that this basically gives you a small constant here. So this is one way to ensure that you don't run into any structural problem with singularity. The second way is to put a boundary. Okay, and this kind of has the same effect actually. So if you think in fluids, what a in inviscid fluids, what a boundary means, it really means that if the vorticity doesn't vanish on the boundary, so say you have vorticity that looks like this, then it really means that the vorticity is actually jumping across this line, right? So if you're putting a boundary here is like forgetting that there's a jump across here. If you have vorticity on the boundary, it's like having a jump on the whole space, which has a very similar effect to having C alpha data. And the third way, which I guess is newer, at least to me, is to consider situations where there's a parity difference. And these two, okay, are kind of, if you're thinking about a lot about this equation, these first two are kind of like cheating. It's very, very good to understand these things, but at the same time, it's important to differentiate between, what's possible in different settings, right? So, in the case of a fluid in the center of a domain, so neither of these issues would really be relevant. Okay. All right. So the second issue that one has to think about a lot when trying to get to prove a singularity. So the second issue is to think about the Biot-Savart law. Right. So the first thing is to think about the structure of the vorticity equation. So how, if you're given a velocity, how does the vorticity evolve? The second issue is, once the vorticity is evolving, how do you understand how the velocity looks, right? So in that sense, you'd want vorticity to evolve in a certain way that grows by velocity looking a certain way. But then if you'd want the vorticity to help the velocity look more like that way that causes the vorticity to grow. So, okay, so what's the Biot-Savart law? So the Biot-Savart law, as we said, it's essentially inverting the Laplacian, right? The key issue, of course, this you take the curl of vorticity first. So this is very important for the issue of parity and all that stuff. But the inverting the Laplacian is sort of the key non-local aspect. So this is a non-local operation. Okay. And so in the last few years, there's a lot of work to try to understand whether you can sort of isolate some main term in this non-local operation. So some simplified operator that's easier to understand that encodes the leading order dynamics. And so the first work in this direction, at least in recent years, was by Kiselev and Shverak, who showed that in a certain geometric situation, the leading order behavior of the so the leading order term of the velocity is given by some simple integral. So I want to explain what that is. So let me just give you the lemma. So let f be L infinity, and let's just assume it has compact support. And Laplace psi is f, so that's the unique solution given by the Newtonian potential. So this is on all of Rd. Then the gradient of psi, so so psi of x minus psi of 0 minus gradient psi at 0 dot x. Right? So this is like the first order Taylor expansion. So remember that when f is just bounded, so I know I'm not going to have enough room here, sorry. We know that when f is bounded, the stream function is, so the solution of this equation is essentially going to be C2, but not really. So there's a correction you have to make. So that's what I'm going to explain now. So psi of x minus psi of 0 minus gradient psi of 0 x. And now we want to subtract a correction so that the remainder is order x squared. So you subtract the integral from x to infinity of the projection to the second Fourier shell in spherical harmonics. So if you think in 2D, it's just the projection to the sine of 2 theta, cosine of 2 theta modes of f. And then you get this kind of simple looking integral, right? So you get, this is the main term, is less than or equal constant x squared. Okay, so this is just reflect for a moment on this this lemma. Okay, so all of this stuff is just the normal first order correction. But it's saying that the psi is essentially determined, so its unbounded part, it's the unbounded part of its second derivative is, okay, so sorry, so this is c x squared f in L infinity, sorry. So if f is just bounded, we know d2 of c doesn't need to be bounded, but its unbounded part is just captured by this simple integral. Okay. So essentially, in scenarios where this might be very large, so for example, in the scenario of Kiselev and Shverak, when they have vorticity, which is, say, on a disk with 1 in this region and -1 in this region, like that, and smoothly to 0, this integral in general is much larger than this. Right? So this can be, if this length is delta, then this integral is larger than log delta, or the version of this integral in this setting. So what I'm stating here is on R2. This is a disk, but okay, it's fine. Sorry. And there's a scaling problem. So it's x squared times log delta. Sorry. Sorry about that. Okay, so with this in mind, you can, okay, and there are other versions of this. So another version, which I'll just state kind of imprecisely, is we know from the Schauder theory that if we take the Laplace inverse, so we take two derivatives of the Laplace inverse, this is a bounded operator from C alpha to C alpha. Okay, so we have to perhaps consider the Dirichlet Laplacian on a smooth domain, but it's a bounded operator from C alpha to C alpha. And the operator norm is like constant divided by alpha as alpha goes to 0. So there's a problem at the integer points, right? And one way of stating this lemma is that in certain settings, this is not true for general functions, but in certain functional setting, you can decompose this into a singular part, which carries this large constant, plus a regular part, which is order 1. And this is going to be uniformly bounded independent of alpha. And S is quite simple. So it takes any function and outputs a radial function. And it's essentially an average in the angles. And you can do this in C1 alpha and C2 alpha. Anytime when you approach the integer spaces with integer index, you have something like this showing up. Okay, so in that sense, if you view the vorticity equation as, so remember that the velocity is determined from the vorticity through this operator. So the gradient of the velocity is essentially second derivative of the Laplace inverse of vorticity. Will be to leading order this simple looking radial operator, which is, it's basically this one right here. So it's some integral in R. So it has very nice properties like comparison principle, other things that you don't think to expect in a singular integral operator. So if you use this, then you can rewrite the vorticity equation in the following form. So you can once you do a change in time. So you can rewrite the vorticity equation in this form. So this is a much simpler equation to analyze. So, by the way, it hasn't been fully analyzed yet in all cases. So very little is actually known about it. But at the very least, what you can say, the gradient of US is always radial.
Mm-hmm.
And
yes, yeah, I do.
What's that? Oh, gradient of US is always radial, and it's some average, like I'm saying. Okay. So so one application of this so there have been at least now 2 applications of this method. So one application is when you have axisymmetric solutions in 3D without swirl. So you consider solutions that are so in 3D they have a symmetry. So the velocity field is invariant. So never O is a rotation matrix fixing the vertical axis. The velocity should be invariant, and the angular velocity should be identically 0. So that's what axisymmetric no swirl means. So that means that particles can move up and down the axis and in and away from the axis. And okay, if you also impose a reflection symmetry about the xy plane, then the equation I just wrote for you guys back here, so this equation becomes the following. So dt omega, so this is now a scalar equation, plus, minus 3/2 L omega sine of 2 theta d theta omega. So this is the transport. So it's just a transport in the angle, and the angle is the angle between r and z, where r is the 2-dimensional radius and z is the third variable, z. So omega is transported and then stretched by following term, so L of omega. Okay, where L of omega is just that operator I wrote on the previous slide. It's just the integral from r to infinity, 0 to pi over 2 omega of s theta over s times some positive kernel k d theta ds. Oops. Right, so this looks strikingly familiar. If you remember from the beginning of the talks, this looks kind of like those one-dimensional equations. And it turns out that you can just solve it. Right now, an important thing that's imposed on us by by axisymmetry is that omega has to vanish on theta's pi over 2. So theta of pi over 2 is the axis of rotation. So the vorticity has to vanish on the axis in order for it to be in order for the gradient of u to be even continuous, right? And now observe that in order for a growth to happen in omega, this has to be positive, right? So if this is positive, then it means that the trajectories in theta are pushing from pi over 2 to 0, right? So sine of 2 theta is, okay, let me come over here. So if you look, it's pi over 2. So pi over 2, this means the axis, right? And theta is 0. This is the plane z equals 0, right? So it means in 3D, so things need to be pushed down like that, right? Or the other way rather. So particles are being pushed down the axis and out in order for there to be growth of vorticity, right? In order for you to have growth of vorticity, particles need to be pushed like that, but they're vanishing here, right? So it means that if if you fix a radius and sorry, they're being pushed this way and they vanish here. They have to vanish here. So means that if you fix a radius and just look at what's happening, so if you have a very strong push from the velocity, so imagine that in order for singularity to happen, this has to become very large. So that means that you have a very strong push toward from pi over 2 to 0 in the angle. So it means that this picture starts to look more like that. And that's precisely because of this number 3, right? So this number 3, what happens is that you have a situation like this: dt omega plus 3x dx omega is equal to omega, right? So this is like Taylor expansion near pi over 2. This is how it's looking. And because omega has to vanish at pi over 2, you observe that dx and omega vanishes at pi over 2. So it's like omega vanishes at 0 in this cartoon here. It means that dx omega, so if you just differentiate both sides, so omega vanishes here, and at the same time, this must decay. Right? It doesn't grow, right? So this decays just by differentiating this equation. You get 3 dx omega on the left side, which gives you a decay at rate of like e to the minus 2t. But then we remember what we said about taking data that's non-smooth in the direction of the flow. So the main direction of the flow here is the angular one. And so if you took a data that doesn't look like that, but looks more like this, right? So it means it's non-smooth at here. Then because this becomes much weaker by taking data like that, then this just blows up. Like even you can just check, like if you take a data that's like x to the 1/4, it vanishes at x equals 0, but under this evolution, so you can solve it on characteristics, for example, it grows exponentially. Right? So in the nonlinear case, when omega grows, L of omega grows, and then there's a feedback and it blows up. Okay, so I've been basically at the end of the talk. I haven't said much yet. Right, so I guess I should make a few remarks on where one should go with this. So one thing, of course, is to think about the case of a domain with boundary. And as I understand it, now there's several groups that are trying to solve this numerically, and I think it seems that this is for smooth solutions within the realm of possibility. And it's, as I said, there's no real structural structure to this, so there's no right. But of course, there is a mathematical obstruction that it's not clear how you actually prove it. Numerically, perhaps it's more doable. Not clear if it's how doable. A second direction, which I think is very important, is to find a new geometric scenario where you really can have a blow up in the center of the domain without using non-smoothness in the direction of the flow and without using a boundary. So an important fact about this blow up is that the data has to be non-smooth at the initial time on a whole axis, right? So in fact, in the paper, it's actually non-smooth on the axis and on the plane z equals 0. But even having even having a singularity from data only non-smooth at a point would be very nice, and it sort of give a different way to get around the sort of structural obstruction to blow up. And okay, in my last 1 minute, I'll just say that another very important problem, I think, and where you can say very little, you can say some things, but very little, is the what happens after singularity. I think this is very important, especially if even in the setting of axis symmetry without swirl, it's maybe possible to that you develop a singularity, but that after the singularity time, there could be a single extension for the solution, which would be very interesting. Or perhaps there's non-uniqueness. But so all of this needs to be figured out. Okay, I went over time, sorry. Thank you.